Hey everyone, today you are going to learn about more of the periodic table. We've already discussed how the periodic table is laid out in certain ways, and that was discovered or developed rather by Dmitry Mendeleev. And the layout of the periodic table is not coincidental. It was devised in a way so that when we look at the periodic table, we can understand based on the position of an element, some of the properties of the atoms of that element. And so for the next couple of classes, you're going to be learning about periodic trends. And periodic trends are one of the things that we can use when we look at the periodic table to do what I just mentioned, know something about atoms of elements, and therefore we can start to predict how those atoms of elements are going to react. So periodic trends, as it says here, allow us to compare elements to each other, and we're looking at their position. And the first periodic trend that we will look at is the trend of atomic radius. And so, as you know, the radius of something circular or spherical is a measure from the center of that circle or sphere to the outer edge. And so when we talk about atomic radius, basically we're talking about the size of the atom, because atoms are roughly spherical. And the size of our atoms is determined by the size of the electron cloud. And so what I'm going to do in the next few slides is explain to you why the electron clouds of atoms are different sizes. And it will, of course, have to do with the electrons themselves. But before we start that, if you take a look here at this table, you can see a layout of the different atomic radii. And so you can see what the trend is, actually, if you look at this periodic table. And before we do that, I just want to mention that the periodic trends are trends. They are patterns that the atoms of elements follow, but they're not perfect patterns. And so if you look at any of the periodic trends, you will see exceptions here and there to the trend, but most times the trend is true. So going down group 1, for example, the alkali metals, we have hydrogen all the way at the top. That's this little teeny tiny atom, and as we go down that group, the atoms get bigger. If we look at going left to right across period 4 here, we see that potassium has rather large atoms, and then as we proceed to the right, the atoms get smaller and smaller and smaller. And so we want to be able to explain why these things happen. So in order to do that, we have to first go through a little bit of vocabulary. Basically, there are two kinds of electrons in an atom. So you know that they're in the electron cloud. The core electrons are all the electrons. And I'm going to use that little E minus symbol for electrons. So this is all of the electrons that are not the outermost electrons. In the electron cloud. And so the outermost electrons, of course, are the ones that are furthest out away from the nucleus. And so core electrons are everything except for those outermost electrons. The valence electrons are the outermost electrons in the electron cloud. And it is the valence electrons that are responsible for chemical bonding. And we're going to get into that a lot as we proceed forward through the year. But let me finish this definition. The outermost electrons in the electron cloud. And then, now that we know there are basically two kinds of electrons, we want to understand a concept called electron shielding. And electron shielding happens when the core electrons block the valence electrons from feeling the pull of the nucleus. So if you think about what is inside of the nucleus, we have protons and neutrons. And the protons having a positive charge are attracting the electrons in the electron cloud. But if there are electrons that sit between the nucleus with its positive charge and the valence electrons, then they're going to block that. So let me finish this definition here. Feeling the pool of protons in the nucleus. And of course, I put the charges of the electron and the proton in these symbols to remind us of that positive negative attraction. So here's our nucleus, and basically all of the electrons in the atom being negatively charged are feeling an attraction to the nucleus because the nucleus has protons that are positively charged. But here in this first layer of electrons depicted here in this picture, these electrons are the core electrons, and they are blocking those valence electrons from feeling that pull. And what adds to that even more is that the core electrons and the valence electrons are all experiencing repulsion between one another because these are all negatively charged. And when you put two negatively charged things close to one another, they don't attract because they're not opposites, they repel. And so those two things together are going to come into play as we continue to discuss these periodic trends. So once again, electron shielding, the blocking of the nucleus from attracting the valence electrons that's happening with these core electrons. And we also have electron-electron repulsion happening everywhere as well. One other thing that I want to mention to you is a concept called effective nuclear charge. And effective nuclear charge is basically a way of understanding the effect of the charge of the nucleus. All right, so it's all there in the name. And it goes hand in hand with what I just mentioned in the previous slide. So here we have two elements, for example, chlorine and magnesium. And chlorine and magnesium, if you look at the periodic table, are both in period 3. But chlorine is on the far right of the periodic table in that row, and magnesium is on the far left. Now, I'm pointing out the fact that these are both in the same period on the periodic table because that period number 3 tells us how many energy levels of electrons are in that atom. So anything in row 3 on the periodic table has 3 energy levels with electrons in them. You can use that same idea for every row of the periodic table, 1 through 7. The number of the row tells you how many energy levels of electrons are there. Now, if we take a look at this, we have our chlorine atom, which has 7 protons in its nucleus. The neutrons are there too, but they have nothing to do with attracting the electrons, so we're not going to focus on them. And then the magnesium nucleus has 12 protons. So now we're going to take all of this information that we've been discussing and piece it together. If we look at the fact that chlorine has more protons in its nucleus, what that means is that the nucleus of chlorine can attract its electrons better than the nucleus of magnesium can attract its electrons. If you want to think of it almost like magnets, all right, if those protons in the middle are magnets and they're attracting something metallic, the more protons or the more magnets there in the nucleus, the more they are going to be able to attract these electrons into the nucleus. And of course, the same here with magnesium, the less protons means the less attraction between the protons and the electrons. So even though each of these atoms has 3 energy levels with electrons in them, it's the difference in the nucleus, the effective nuclear charge, that in rows on the periodic table determines how big or how small those atoms are. So I just want to really drive home the point here that right now we are specifically focusing on atoms in the same row or period on the periodic table. Okay, so now that we have that background, now we're going to talk about the trends. So starting with atomic radius, the trend is that the further we go down a column or group on the periodic table, the larger the atomic radius. And the further across a row, going from left to right, the smaller the atomic radius. and we need to talk about why. And you guys need to be able to explain why. And so make sure you are listening up, because once you know why for one of the periodic trends, it works for all of the periodic trends. So here we go. Why are atoms bigger as we go down a group? As we go down a column or group, the electron cloud gets bigger because energy levels are being added to the atoms. Think about what I just said a few moments ago. Every row on the periodic table indicates another energy level of electrons being added. So if we're talking about the first row of atoms, there's one energy level. And I'm going to use the Bohr model of the atom here, even though we know that our modern model doesn't have rings in it, but my rings are representing energy levels. If we're in the second row of the periodic table, there are 2 energy levels of electrons. The third the third row on the periodic table means we have 3 energy levels of electrons, and so on, all the way up to 7. And so going down a column, we would see just more and more layers of electrons being added. And remember what's happening. Every time we have a new layer of electrons, we have that repulsion happening between electrons. So the more energy levels that we add going down a column, every step of the way, that atom gets larger and larger. Now, what about going across a row? We just got done talking about effective nuclear charge. So as we go across a row from left to right, the effective nuclear charge, or the charge in the nucleus, gets stronger, and the electron cloud is pulled closer to the nucleus. So I'm going to redraw that example that I did of magnesium and chlorine. If this is my magnesium atom, remember it's in the third row on the periodic table, so it has 3 layers of electrons. My chlorine atom, which is on the far right, still has 3 energy levels of electrons, but it is smaller. And the reason, remember, is because the nuclear charge of chlorine is 17. There are 17 protons in there, whereas the number of protons in magnesium's nucleus is only 12. And so going from left to right, our atoms get smaller. So now I want you to pause the video and try to answer these questions. And when you think you've finished them, unpause, come back, and see if you got them right. All right, so let's see how you did with these questions. The smallest halogen, remember the halogens are group 17 on the periodic table. So groups, of course, go up and down. So we're talking about that column, and atoms at the top are smaller because they have less electron levels to cause electron shielding. And so the smallest halogen is fluorine. The largest actinide, the actinides are the very, very, very bottom row of the periodic table, of that subset that's pulled out to the bottom. And the largest one, when we talk about that, we have to consider that we are looking at a row of elements. And as we go from left to right, the atoms get smaller. So the largest atom would be on the furthest left of that row. And so that is TH, thorium. Number 3, the largest transition metal. Transition metals are groups 3 through 12. So we have basically like a rectangular shape of the periodic table that we are considering, lots of elements here. But we want the largest transition metal. So if we remember that atoms get larger as we go down, and atoms get smaller as we go to the right, that means that we want to go to the bottommost row of transition metals, and we want to go furthest to the left, because as we go to the right, they get smaller. And so we're looking at the element actinium in row 7. The largest atom on the periodic table, same reasoning that we just used. We go all the way to the bottom of the periodic table because that's where the largest atoms are, and furthest to the left, and that atom is francium. And the smallest of nitrogen, silicon, and gallium. If you look at these elements, they're in a diagonal line. We know that as we go up, elements get smaller, and as we go to the right, elements get smaller. And so the smallest of these is nitrogen. It is the furthest up on the periodic table, and it is the furthest to the right of these three. So now that we've done a bit with atomic radius, we are going to look at ionic radius. Atomic radius and ionic radius are very close to one another, as you can imagine. There's only one difference here. We're talking about the radius of an atom versus the radius of an ion. Remember, an ion is an atom that has lost or gained electrons and now has a charge. So just a few bits of information about ions. Anions are atoms that have gained electrons, and in general, they are bigger than the atom that they are made from. And they are made from nonmetals, and as I already mentioned, they do have a negative charge. Cations are the other kind of ions that we talk about, and these are atoms that have lost electrons. Cations are smaller than the atom from which they are made, and they're made from metals and have a positive charge. The way I tell students to remember this is that cats, or cations, have paws. You can even draw yourself a little cat paw if you want. This isn't the world's best cat paw, but there it is. All right, cats have paws, and I've had students in the past say that they relate the word anion to the word onion because onions make you cry, and crying is negative, and that's how they remember that anions have a negative charge. So we are going to talk again about the size of the electron cloud when we look at these atoms, or excuse me, these ions compared to the atoms that they're made from. So here we see a diagram just showing us over here on the left-hand side, we have pink for the cations and gray are the atoms that they're made from, and you can clearly see that cations are smaller than the atom that they're made from. On the right side over here, we have anions, and they are blue, and the anions are bigger than those gray atoms that they are made from. Now, the trend in the size in general, the further down a column we go, the larger the ionic radius, and the further across a row, going from left to right, the smaller the radius. Now, the Y. The Y is the same as it was for atomic radius. As we go down a column, the electron cloud gets larger because energy levels are being added. It doesn't matter that these are now charged atoms that we're talking about. We are still dealing with the fact that going down a column, we have atoms with one energy level of electrons, and then the next step down would be 2 and 3 and so on, all the way up to 7 energy levels. So going down, that electron cloud gets larger, so the ions also get larger, going from the top to the bottom of a group on the periodic table. And guess what? Going left to right across a row, there's the same pattern as with atomic radius as well. The effective nuclear charge increases going from left to right across the periodic table, and so the atoms on the right, when they turn into ions, have the same smaller size as they did before when they were atoms. And so again, ions on the left of the periodic table are larger than ions on the right of the periodic table. So go ahead and pause the video one more time, check out these 5 problems, and when you are done, come back and check your answers. Okay, we have a variety of questions here. Number 1 says, which is larger, the fluorine atom or the fluorine ion? This charge up here as a superscript tells us the charge of the ion. So we went from an atom to an anion. That means it gained an electron, and so it is larger than the atom that it comes from. Of magnesium and the magnesium plus 2 ion, the ion is smaller. Remember, cations are smaller than the atoms that they're made from. Now, number 3, of sodium, potassium, or rubidium, which is the largest of those ions? If you look at the table, periodic table, sodium, potassium, and rubidium are in the same column. And for groups, we know that as we go down the group, there are more energy levels of electrons, and so the ions are bigger. So therefore, rubidium, which is the furthest down of those three, is the largest. Of nitrogen, oxygen, and fluorine ions, which is the smallest? I want to point something out to you before we talk about the answer to this question. The magnitude of the charge here, -3, -2, or -1, does not matter. Okay, that number up there does not matter. What matters is that these atoms have all gained electrons to become anions, but the amount of electrons that they gain will not affect the size of the ion. And so when it comes to determining what is smallest, if we look at the periodic table, we'll find our answer. Nitrogen, oxygen, fluorine are in the same row. Nitrogen is furthest to the left, oxygen is in the middle, fluorine is furthest to the right. And fluorine, being furthest to the right, has the greatest effective nuclear charge, and so therefore it has the smallest ions. Lastly, the smallest of aluminum, gallium, and indium. Here we have 3 ions in the same column. They each have the same charge. And so if we're talking about size, we're going to think about how many energy levels of electrons do these have. Aluminum, being up the highest in the group, has the least amount of energy levels, so it is the smallest ion of those 3.